I am going to discuss spaceship paradox in theory of relativity, commonly known as Bell's spaceship paradox. Here is the scenario. There is an inertial frame S. Relative to this frame, two spaceships A and B are moving at equal velocities. They are connected by a taut string. The string is so delicate that if it is stretched even a little, it will break. As seen from frame S, the two spaceships simultaneously receive equal accelerations. Their speeds increase due to getting accelerated. The question is, does the string break? Here is the paradox. As seen from frame S, the speeds of A, B and the string increase. Due to length contraction, the string's length should decrease. But A and B always have equal velocities. So in any given time interval, A and B cover equal displacements. Therefore, the distance between them should remain a constant. The string's length has to decrease, but the distance between the spaceships does not change. This means the string breaks. But the string will break if it is stretched. The distance between the spaceships A and B does not change. So how is the string getting stretched? Fix a frame of reference on the spaceship A before this spaceship gets accelerated. Call this frame as S prime. In frame S, assume that the string is attached to A at x equals 0 and to B at x equals d. Also in frame S, both the spaceships accelerate together. Assume that they both accelerate at time t. And in frame S prime, assume that A accelerates at time t1 prime and B at time t2 prime. We use Lorentz transformation to find the relation between t1 prime and t2 prime. So we use the transformation formula to find t prime in terms of t and x. To find t1 prime, we put x equals 0, and to find t2 prime, we put x equals d. As we can see, t2 prime is less than t1 prime. This means, as seen from frame S prime, B accelerates before A. We show the same thing without using the transformation formula and purely using the concepts so that the concepts are clear. Assume that the frame S is fixed on a third spaceship which is equidistant from spaceships A and B. S sends a signal 1 to A which accelerates when it receives the signal. Similarly, S sends a signal 2 to B which accelerates on receiving the signal. As you can see in the diagram, A and signal 1 are approaching each other, but B is trying to move away and the signal 2 catches up with it. This means signal 2 has to cover a longer distance than signal 1. Now both the signals are moving at the same speed c and both have to reach their respective destinations together. But if signal 2 has to cover a longer distance than signal 1 and both the signals are moving at the same speed, how is it possible that they will reach their destinations together? This can happen only if signal 2 originates before signal 1. In frame S prime, both A and B are at rest before any of them accelerates. In this frame, both signal 1 and signal 2 have to cover equal distances because the spaceships are not moving. This means the signal that originates earlier will reach its destination earlier. And as we saw, signal 2 originates before signal 1. This means signal 2 reaches spaceship B before signal 1 reaches spaceship A. The spaceship B accelerates before the spaceship A. As we saw, In frame S, both the spaceships accelerate at the same time. But in frame S prime, the front spaceship accelerates earlier. And as you can see, as seen from S prime, A and B are at rest, which means that the distance between the spaceships as seen from S prime is the proper distance. Since in this frame, the front spaceship accelerates earlier, therefore the proper distance between the spaceships increases. This means the string gets stressed and it breaks. However, the paradox is still not completely resolved, because if the string breaks as seen from frame S prime, then it must break as seen from frame S also. The string will break if it gets stressed. In frame S, the distance between the spaceships does not change. So how is the string getting stressed? The answer is that the distance remains constant because of the string getting stressed. See the length contraction, or you can say distance contraction formula here. Here d is the distance between the spaceships relative to frame S. D naught is the proper distance between the spaceships. As the spaceships accelerate, v increases, and we are assuming that d does not change. Now d remains constant and v increases. This is possible as seen from the distance contraction formula only if the proper distance d naught increases. So proper distance is increasing. This means the string is getting stressed. Now because of increasing d naught, the distance should increase. But because of length contraction, the distance should decrease as seen from frame S. Now the effects of increase in proper distance and of distance contraction are exactly compensating each other, and this is how d can stay constant. We found that as seen from any frame, the string will break. But what is the real cause of the string breaking? As seen from frame S, does the string break due to length contraction? The answer is no. Using the concept of length contraction, we can conclude that the string will break, but length contraction is not the cause of the string breaking. Length contraction is a coordinate transformation. It has no real physical effect on the string. So the question is, why does the string really break? The answer is, in any of the frames, the actual cause of the string breaking is that it gets stressed and the tension in it increases. What happens to the spaceships? In frame S, the length of each spaceship is less than its proper length according to length contraction. But this length contraction has no real physical effect on the spaceships. The astronauts inside the spaceships will not notice the length contraction. What will happen if we use a strong rod instead of the string? In this case, it is very difficult to make sure that the distance between the spaceships is a constant as seen from frame S, in which the spaceships are moving. Instead, the entire assembly of the two spaceships and the rod in between will shrink as seen from frame S. That is, the entire assembly will undergo length contraction. But if we can somehow manage to keep the distance between the spaceships constant in frame S, then the rod will also get stressed. Thank you. Please subscribe to my channel and like this video.